Organic Chemistry 1. Introduction. Alkanes and structural isomers. The essential idea. Well, organic chemistry focuses on the chemistry of compounds containing carbon. Nature of science. Serendipity and scientific discoveries such as PTFE and superglue. Ethical implications. Drugs, additives and pesticides can have harmful effects on both people and the environment. Serendipity means good luck, and superglue, I believe, was invented twice, or discovered two separate occasions just by good luck. And obviously, you probably read a great deal about the downside of drugs and pesticides, and there's just obvious upsides to both too. International mindedness. A small proportion of nations have control of the world's oil resources. The interdependence of the countries that are net importers and those that are net exporters is an important factor in shaping global policies and economic developments. These you would do in a class if you were in class. Some fundamental concepts. There are an estimated, what is that? It's 1 billion or so different organic compounds. All of these compounds contain carbon. It's a very, very versatile element. So what's so special about carbon? Why is it so versatile? Well, carbon can form either single, double or triple bonds with other carbon atoms or with atoms of other elements. You can see over here, there's a single line between these two carbons, there's a double line between these two carbons, and there's a triple line between these two carbons. As you probably guess, the single line indicates a single bond, double line, double bond, triple line, triple bond. The single carbon-carbon bond is very stable. It is more stable than bonds formed between the other group forming elements. You can see here it has a higher average bond enthalpy, and you will find out what that means later on in your exciting chemical or chemistry journey. What's so special about it? There's other things that are special about it. It can form stable long chain straight, let me say that again, can form stable long straight chains, branch chains and ring structures. You can see this polyethylene molecule and the very long carbon chain running through it there. Here you can see this beautiful ring structure, glucose, which we use for respiration, and we put in our coffee or tea if you're a Philistine, and cholesterol. And you can see here cholesterol, we've got some ring structures and you've got a bit of a long chain going on there too. You also got some double bonds here, and you've got a whole bunch of single bonds. A homologous series is a group of organic chemicals with the same general formula, such as alkenes. Their general formula is CnH2n. So if they had two carbons, can you guess how many hydrogens it would have? Yes, of course they'd have 4. Successive members differ by CH2. For example, the first 4 members of the alkenes. C2H4, just add 1 to the 2, you get C3, it'll be C3H6, C4H8, C5H10. That can go on indefinitely. Chemical properties are the same for all members. So all alkenes are combustible and they react readily with bromine. And 4, physical properties gradually change as you move along the homologous series. For example, the boiling points of the alkenes increase as the chain length increases. So those 4 things, same general formula, they differ by CH2, chemical properties are the same for all members, and physical properties gradually change as you move along a homologous series. Here's some examples of common homologous series. You'll have heard of some alcohols, others probably not. You may not have heard of carboxylic acids or nitriles or ketones, but you will be an expert at all these in a very short space of time. Nomenclature and structures for hydrocarbons, the basics. Hydrocarbons are obtained from crude oil. So you get oil from the ground in its raw state, and then you can separate it out into different things. It has many uses. Hydrocarbons are used as fuels, obviously, petrol, diesel, etc. They're used as plastics. You may enjoy drinking from plastic cups or using plastic forks. And they're precursors for food additives, dyes, pharmaceuticals, fabrics, and so many more things. It's crazy. They're in everything, and that's why oil is so expensive and why people go to war for it. Homologous series of hydrocarbons. Alkanes. They have single carbon-carbon bonds. Their general formula is CnH2n plus 2. So if you had C2, H would be, can you guess? That's right, it would be 6, because 2 times 2 is 4, 4 plus 2 is 6. Alkenes. At least one double carbon-carbon bond. The general formula is CnH2n, and we did that earlier, so I'm not going to do it again. Alkynes. Oh, that's a good point. This formula only works if there is only one double bond present in the molecule. Sometimes you might get a very long molecule that has a couple of double bonds in, like some fatty acids. Alkynes. At least one triple carbon-carbon bond. The general formula is CnH2n minus 2. So if you had Cn2, can you guess what the H would be? Can you work it out before I do? That's right, it would be 2. Because N is 2, so plug it in there. 2 times 2 is 4. 4 minus 2 is 2. Again, only works if there's only one triple bond present. Won't work if there is more. The names of all hydrocarbons must include a stem and a suffix. You need to become an expert at IUPAC nomenclature for hydrocarbons. Okay, nomenclature is just another fancy word for name. Okay, you've got to use the correct language when we're speaking about chemistry. We use the IUPAC system for naming stuff. So stem and suffix. The stem goes at the front. Suffix goes at the end. Meth, ein, eth, een, prop, ein. The stem tells you the number of carbons in the longest chain. So, meth has 1 carbon, eth 2, prop 3, bute has 4 carbons in it, pent, hex, hept, oct, and non-dec, undec, dodec. If someone was dodec-ane, it would have 12 carbons. If someone was hept-ene, it would have 7 carbons. Some people like to think about monkeys eating peeled bananas to remember the first 4. I promise you that the first 8 will be seared into your memory within 2 years. The suffix tells you the homologous series. So the bit at the end tells you which homologous series it belongs to. Ein is an alkane, een, alkene, ein, alkyne. Easy to remember because endings are the same as the name they come from. Try these, please. You can't try these, can you? You've got no idea how to do it, so I'll do it for you. Propane. Why is it propane? Well, 1, 2, 3 carbons, so it's prop. And all the bonds between the carbons are single, so it's an alkane, so ane, propane. Next, we've got 1, 2, 3, so it must be prop again. And we've got a triple bond there, so it must be ein, propyne. Here, 1, 2, so it must be eth, and has a double bond, so it's an alkene, So ethene. Haha. Many hydrocarbons contain branches or shorter carbon chains. Let's have a look at this. You see, you've got this branch here, a methyl group. I'm going to turn this fan down because it's going to get really loud. The branch name follows this pattern. You've got the stem plus -ile. So just looking at this here, there's one, so it's going to be meth, because there's just one carbon in the branch. And you stick -ile on the end, methyl. If there'd been two carbons, if it had been C2H5, it would have been ethyl, because it would have been a two carbon branch. 3 propyl, etc. The branch name and position is added as a prefix to the name of the longest carbon chain. Prefix means you stick it in front. So this bit would go before the name of the whole thing. Number the carbons in the longest chain starting from the end closest to the branch. You can see this is the branch, so this would be one end, this would be another end. You can see a little 5 there already. I don't know what that's doing there, but it helps you because obviously this is going to be carbon 1. This carbon is nearest to the branch. So then we add the branch name as a prefix. So we're going to add this branch name in front of the name of the longest chain and use a number to indicate the carbon with the branch. Well, we're going to see the number is going to be 2, don't we? So we've got 2 because the methyl group is attached to the second carbon. 1, 2, 3, 4, 5 in the longest chain. So we've got pent. And they're all single bonds between the carbons. So it's ane. 2 methyl pentane. Notice the dash. Always separate numbers from words with this hyphen. If there are more than 2 branches of the same length, add a prefix before the branch name and indicate the position of both branches. So let's have a look at this one. We've got this methyl group here, and you can see it's on the second carbon. Oops, it's just giving it away. That's no good. It was in the wrong order. You've also got this methyl here. Yes. You can see the chain is 1, 2, 3, 4. So you've got methyl branches. You've got 2 of them. So you write di for 2, di, methyl, and the butane, 1, 2, 3, 4. So the carbon chain is 4, butane, and we're going to say where the 2 methyls are, 2, comma, 2 for the position of these both, and then our hyphen, 2, 2 dimethyl butane. This one below, we've got a methyl chain there. Let's number them. 1, 2, 3, 4. The longest chain is 4 long. And we've got another one here though. So this time we'll have to write down, it's going to be butane, isn't it? We've got our butane written there. We can see there's 2 methyls, so we'll have to write our methyl. We've got 2 of them, so we need to write it's di. Then we've got to write the numbers 2 and 3. 2, comma, 3, hyphen, 2, 3 dimethyl butane. Have a go at these, please. Press pause, pause. Really do, really press it. And then don't start again until you've had a good go. The struggle is everything. It's what makes your brain work. Okay, this would be 3 methyl pentane. Why? 1, 2, 3, 4, 5 pent. All single bonds. Ane. The only branch has 1 carbon. Methyl. It's on. We'll start either side because 1, 2, 3 or 1, 2, 3. This is always going to be carbon 3. So 3. This one, the longest chain is 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Okay, so this chain here would be 7, or this chain here would be 7. So it doesn't matter which way you start the chain, the longest linkage of carbons is going to be 7. So we know it's going to be heptane. Okay? So let's write the heptane down. You can see we've got the methyl here, and we're going to put that on the nearest one, so it's going to be 1, 2. Okay, this is the one nearest to an end, so 2 methyl. Then let's count along. 1, 2, 3, 4, 5. On the 5th carbon, we've got a branch of 2, which is going to be ethyl, and it's on carbon 5. So 5-ethyl, 2-methyl heptane. You'll get this with practice. Don't worry if you haven't a clue what's going on. This, you learn this by practicing practice of problems. The carbon atoms in an alkane may be arranged in a ring structure. Name the cyclic alkane by adding cyclo as a prefix. Cyclobutane. Well, there's 1, 2, 3, 4. So but. They're all single bonds, so ane. And it's in a cyclic ring structure, so cyclobutane. Over here, what have we got? We've got methyl cyclopentane. So you can see the ring here has 1, 2, 3, 4, 5. So pent. It's got all single bonds, so ane. It's in a cyclic ring, so cyclo. And it's got one bit sticking off, methyl, because it's only got 1 carbon. Down here, 1, 2, 3, 4, 5, 6. Got a ring of 6. Look, we've got 2 methyls. We know it's going to be a dimethyl thing. 6 is going to be hexane. We know it's cyclic, so cyclo. So we've got the 6 carbons, all single bonds, so hexane. See, it's cyclic, so cyclo. You can see they're both methyl, so methyl. The 2 of them, so di. And the numbering system is you pick one, so like just which has a methyl group on it. Let's just call that 1, and then just count the nearest numbers to the next one. So it'll be 1, 2, 3, 1, 3. Dimethyl cyclohexane. You wouldn't count the other way. If you'd arbitrarily call this one 1, you wouldn't go 2, 3, 4, 5. You also have the smallest possible numbers in a ring structure. Molecular, empirical, and structural formulas. So there's 3 types of way of writing formulas. Molecular formulas, it shows the actual number of each atom. So C4H10, it's just showing you how many atoms you have. This molecule here has 4 carbons, 10 hydrogens. Empirical formula. This shows the lowest ratio of atoms. The lowest ratio between here as whole numbers would be, if you divide both by 2, it'd be 2 and 5. The structural formula shows all bonds and atoms. So we've got the 1, 2, 3, 4 carbons, and we've got all those hydrogens bonded. You'll have to make sure that all carbons have 4 bonds. And you can see this one here has 1, 2, 3, 4. This one here has 1, 2, 3, 4. So it's all good. And you'll see in sometimes on websites and maybe in some books that people don't draw the hydrogens. This is not allowed in IB papers. So just get used to drawing the hydrogen atoms all of the time for structural formulas. Okay? Complete versus condensed structural formulas. So you can draw structural formulas as a complete one or a condensed one. For straight chain molecules, it's fairly straightforward. You've got the complete structural formula here for propane. 1, 2, 3, prop, all single bonds, ane. And then this CH3 becomes CH3, this CH2 becomes CH2, and this CH3 It's just written as CH3. Easy. What about pentane? Exactly the same. You've got CH3 here. So you just write it there. Then you've got 1, 2, 3 CH2s. CH2, CH2, CH2. Then you've got the CH3 on the other end. CH3. You could also write this another way. You can put these CH2s together. Okay? You can write them in a bracket there. So successive CH2 units in a chain may be written like this within a bracket. And it'll always have a little 2 there. Okay? That's the thing to remember. Inside a bracket, it's a little 2 if you're just using a shorthand technique. You can use brackets for other things. And we're going to find out exactly what that other thing is here. So, the complete versus condensed structural formulas if you've got a branched molecule. We've got 3-methylpentane here. And this is how you draw it. Okay, so you've got your CH3 here. There. Then CH2. There. Then you've got CH. Here. And then you've got your branch. Right there, look at it. And that's written inside the brackets. Then you've got your CH2 and you've got your CH3. Your CH2 and your CH3. Branches are shown in parentheses. Notice the methyl branch is CH3, not CH2 like we saw last time. For some special cases, you see these skeletal structures. You'll see them again on websites and in books. And what they basically do is every beginning and change in direction is a carbon, and you just emit all the hydrogens. So this line here means the same thing as that. Okay, you just don't draw you don't write carbon, you don't write hydrogen at all, and it's just assumed, people know that this carbon there would have 3 hydrogens on it, and it's assumed that this carbon here has 2 hydrogens on it, etc. 2-methylpentane will be drawn like this, and 1,3-dimethylcyclohexane would be drawn like this. Okay, sometimes you would see it. Let me just get this right. Like that as well. You wouldn't even have the methyl groups on top of it. Okay, press pause. Really press pause. Actually press pause right now and fill this in. Okay, let's see if you got them right. Butane. You've got 1, 2, 3, 4, and all single bonds. You've got 2-methylhexane. So we've got 1 carbon, then look, it's a CH2, so this is just a chain of CH2s, and there's 3 of them. So 1, 2, 3, 4, 5, 6 carbons in the chain. This bracket here, it's a little 3, isn't it? So this is a branch, so you wouldn't count it when working out the hexane bit. But of course, we do know that we write it as methyl because it is a branch, and we know that it's nearest this one, so it's the second carbon along. It's going to be attached to this CH. The other bond for this one is attached to this. So 2-methylhexane, 3-ethylpentane. Did you get this? Well, we've got pentane, so 1, 2, 3, 4, 5. Pent is 5. 3, so put on the third carbon. 1, 2, 3. It's going to be attached to this carbon, so CH. The carbon's other bond is attached to whatever's in this bracket. It's ethyl, so C2H5. What about this one? Did you get that? Obviously, it is going to be butane because you've got 1, 2, 3, 4. Not inside the brackets. And we can tell this is a branch because it's CH3 in there. So butane, we can see there's 2 methyls because a little 2 there, telling us there's 2 things, 2 branches. So dimethyl, and it's on the 1, 2. It's on the second carbon, so 2, 2 dimethylbutane. What about this one? A bit harder. Did you get it? 1, 2, 3, 4, 5 carbons. Pent. Because there's no double bonds or triple bonds, and the branch is ethyl. Now you're probably saying, 1 minute, wait, how dare you? Why didn't you write 1, 2, 3, 3 ethyl pentane? Well, you could have, but if this ethyl group had been moved here, it would be a totally different molecule. Okay, and so this is all it could be. If you'd wrote 3 ethyl pentane, you would not be penalised for that. Down here, I'm sure you all got this one, because there's just 4 carbons and all single bonds, and it's a nice cyclic structure, cyclobutane. Another special case, stereochemical structures. Again, you'll do a bit more of this later on. But carbon atoms that bond to 4 other atoms have a tetrahedral shape. The stereochemical structures show the 3-dimensional arrangement around an atom. So just a special way of drawing, in this case, methane. The solid lines here are in the plane of the paper. So you imagine these just being in the plane. So the carbon and the hydrogen would be imagined to be stuck onto the paper. They'd be flat on the paper. This hydrogen here, attached to the wedge, you imagine that coming towards you. So this is coming towards you. It's in front of the plane of the paper. And the dashed line here, this hydrogen, you imagine it being behind the plane of the paper. So, structural isomers. Same, but different indeed. What is similar about these molecules? What's different? Press pause, see if you can work it out. Pause. Okay, I'm sure you got it. They have the same number of carbons and the same number of hydrogens. Therefore, they've got the same molecular formula, C5H12. However, the length of the longest chain and the number of the branches is different in each one. So the longest chain here is 1, 2, 3, 4, 5. Longest chain here is 1, 2, 3, 4. Longest chain here is 1, 2, 3. So they've got different structural formulas, and therefore they'd have different names. So same molecular formula, different structural formula. Molecules with the same molecular formula but different structural formulas are called isomers. More specifically, they are called structural isomers when the structural formula is different due to changes in bonding patterns. You can see some structural isomers here. C5H12, you have 5 carbons in a row, nice chain, or you can have 4 in a chain and you have 1 branch, or you could have 3, 2 branches. Structural isomer C3H6, you can see you can have a cyclic structure, or you can have an alkene here. So an alkene and an alkane with the same molecular formula obviously would have different structural formulas. Here you can see that the difference is that they are, oh man, let me go back. Here the difference is that the double bond is just in a different place. It's in the middle there between 2 and 3. Here it's between 1 and 2. So these are all structural isomers with the same basic formulas. Right, have a look at this. A student draws these structures as examples of structural isomers of C7H16. How many unique structural isomers are shown? Right, press pause and have a go. And really do it, press pause. This is how you learn things, by using your noggin. Okay, check your answers. You can see A and D. 1, 2, 3, 4, 5, 6, 7 in a row. D. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 in a row. Yes. B, F, and C all had a chain of 6 with 1 methyl, and you can go back and check that if you want. Okay, we've got a chain of 6. Notice it doesn't matter how you draw it. You don't also have to have the chain drawn in one long line like it is up here. It can bend at the end, or it can bend here and the branch can be sitting on the end. Okay, so don't be caught out by that. And E and G with the same. You've got 2 dimethyl structures. You've got a methyl group there, methyl group there. and you've got a methyl group here, a methyl group here, got a chain of 1, 2, 3, 4, 5, a chain of 1, 2, 3, 4, 5. Again, it doesn't matter how it's drawn, just follow the longest chain. Find the longest chain first and then look for branches. Oh, it goes through it here, look, didn't realise that. Let me just, I want to put all these on, give us a second. Oh, it's basically going through what I just did. So, once again, to be clear, draw in, if you've got a structural formula, put a light line, but using a pencil if you need to, of the longest chain. And remember, the longest chain might seem like the longest chain should be flat. It's not, it's just what is connected. This is poorly drawn. That little line should have gone to the carbon. Here, you've got the longest chain of 6. And you've got the methyl group on the 3rd carbon. And this is drawn out how you might want it to be drawn out. Here, it's exactly the same thing, but the methyl group is just above rather than below. Here is where it gets a bit tricky. You think, oh, this, when you might not have realized this one, but quite clearly this carbon is attached to this carbon, 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 is attached to this carbon. There is a carbon chain of 6. And then you just number them, starting whichever one is nearest the branch, this branch being here this time. And it's on carbon 3, so again it'll be 3 methyl hexane. And down here I did go through that quite clearly before. Okay, I would like you now to draw and name the structural isomers with the molecular formula C6H14, and you can show me them when you get the chance. That's the end of this presentation. Splendid.